Hey, welcome! Today, we're going to dive into a really cool concept in chemistry called electron affinity. Basically, it's all about how much an atom really wants to snatch up a new electron.
So, to get our heads around this, let's start with a word you might not expect to hear in a chemistry explainer: love. Seriously, what does it mean for a tiny, tiny atom to have an attraction, or a love, for an electron? Let's figure that out.
At the very heart of this whole thing is this idea of attraction. It's a simple concept, but it's incredibly powerful when you think about it on an atomic level. And this isn't just me being poetic. The source material itself actually uses this exact language. It describes electron affinity as a love or attraction for accepting an electron. I think that's a great way to picture the powerful forces that are always at play inside an atom.
But here's the catch. Just like in life, right? This attraction isn't the same for everybody, or, in this case, for every element. Every single element you see on the periodic table has its own unique personality, its own level of desire for grabbing a new electron. Some are, absolutely desperate for one, while others, they could pretty much take it or leave it. Okay, so picture this. A new electron shows up on the scene. What actually happens? Well, it's not just one thing. It's a dynamic, step-by-step process. It all unfolds in 3 key steps. First, a free electron wanders into the neighborhood, right near the atom's outer shell. Then, the atom's nucleus, which is positively charged, acts like a powerful magnet and just pulls that new electron right in. And the grand finale of the successful capture, a burst of energy is released. So an atom attracts an electron, and this whole event releases energy. Now that's a huge clue for us. But how do scientists actually measure this attraction? I mean, how do you put a number on an atom's so-called love for an electron? Well, here it is, the big reveal. This is the formal, scientific definition. Electron affinity is how we measure that exact amount of energy that gets released when a neutral atom, in its gaseous state, successfully gains an electron to become something we call an anion. And of course, scientists have a specific way of writing this all down. First off, they keep it simple. The symbol is just EA. Now, here's a key part. The value is always a negative number. That's just the universal sign in chemistry for energy being released. Think of it like the atom is so thrilled to get that new electron, it celebrates by giving off a little burst of energy. And we typically measure that energy in a unit called kilojoules per mole. All right, let's talk about the final outcome. The atom has snagged a new electron, it's released some energy, but what does it actually become? What's its final form after this whole transformation? And this is a huge deal. The atom isn't neutral anymore. Because it gained a negatively charged electron, the whole atom now has a net negative charge. And we have a special name for a negatively charged atom. It's now an anion. This whole process is a really crucial first step in how tons of chemical bonds are formed. So let's do a super quick recap. It all starts with an atom's attraction or affinity for a new electron. That attraction is so strong that when it grabs one, it actually releases energy. We can measure that released energy, and that's how we quantify electron affinity. And the end result? A neutral atom transforms into a negatively charged anion. Simple as that. Okay, I want to leave you with one final thought to chew on. We've just seen that gaining an electron releases energy, right? So, what do you think happens in the complete opposite scenario? What kind of energy change do you think occurs when you try to force an atom to give up one of its own electrons? Just something to think about. Thanks for digging into this explainer with me.